but this is equal to minus half into 1 by xj to the power 3 by 2 into, this is a product rule. Okay, so I will have 2 times xj into del I xj. Okay, so I will get 2 terms which are identical to this. Now, this 2, of course, we can cancel with this 2. But what is del I xj? So what is this term? Del I is a shorthand notation for dou. This del I is basically equal to dou by dou xi. Correct? So when I take dou by dou xi, if j is equal to I, it will be 1. Otherwise, it will be 0. Correct? So this quantity here in the bracket, whatever I have written, this quantity is delta I. So that gives you have minus xj delta ij divided by xj to the power 3 by 2. But what is xj delta ij? J is dummy, right? So that means you have to sum over j. If you sum over j, only when j equal to I, it will survive. Rest of the terms will be complete. That means you have this one to be minus xi divided by xj to the power 3. But what is minus xi? Minus xi is just index notation for the vector r. So this is same as r by modulus r, the whole cube with a negative sign. So this is how you can find out, do a calculus of any calculus in this notation. Okay, so this is one thing which is very useful. So let me just illustrate this, how this is used in so-called in electrostatics or also in magnetostatics. In electrostatics, we have something called multipole expansion. So what that it has got to do with that, if you have a potential, electrostatic potential, which I am sure you all remember, is 1/4 pi epsilon naught integral rho of r prime into d3 r prime divided by modulus of r minus r prime. So this corresponds to a situation where you have some coordinate system and there is some kind of a charge distribution here, and this is a representative point r prime for the charge, and you are interested in finding out the potential at a point r. And this distance, this vector is r minus r. Okay, so this is the potential. Now, you can do this multiple expansion in many ways. One of the ways is, of course, you try to expand this using addition theorem of spherical harmonics, but I will try to do it differently so that we can use this index notation. So for that, let me let me tell you that if you have a function, let's say a function x plus some a, okay, it can be expanded in Taylor series, f of x plus a df by dx plus a square by factorial 2 into d square f by dx square, and so on. Now, this can be written in the following fashion. This is 1 plus a d dx plus a d dx the square by factorial 2, and so on. This whole thing is like an operator operating on f of x. So one can write this as e to the power a d by dx, because this is an expansion for e to the x operating on f of x. So if you want to translate the argument of a function by an amount a, you operate it on this. This is called translation operator. Since d by dx is related to momentum, in quantum mechanics, translation operator is written in terms of the linear momentum operator. Or in other words, generator of translation is linear momentum operator. Okay, but that's not our business here, so let's not go into quantum mechanics. Now, if you have this operator, now I can generalize this. Suppose if I have a function, okay, so generalize it to vector function. So if I have, let's say, some capital F of R, which is displaced by some epsilon. Now, it's not very difficult to realize that this will be equal to epsilon dot del. This is the operator acting on the property. Okay, so it's very easy to do this because you now write down x plus epsilon x, x plus epsilon 1 plus x plus epsilon 2, y plus epsilon 2, z plus epsilon 3, like that, and do a Taylor expansion in each of the variable. Okay, so you can realize. So I will leave this for you to work out. Okay, proof. You write this proof. Okay, but this can be written in this fashion. And once we know we can write it in this fashion, then I would like to say that, so now apply this. Apply this to 1 by r minus r. So I would like to consider this as a displacement from 1 by r. So 1 by r minus r prime, I would like to write it as e to the power minus r prime dot del acting on 1. Okay, so this 1 over r is displaced by r minus r prime, and this is the operator which does that job. Okay, so far so good. So now you go back to your potential and substitute this one. Okay, so let's go back to the potential. So phi of r is equal to or is equal to 1 by 4 pi epsilon naught into integral d3 r prime rho of r prime into e to the power minus r prime dot del acting on. Okay, so this I can do it in the following way. So this is 1 by 4 pi epsilon naught integral d3 r prime rho of r prime. And this one I will write it as 1 minus r prime dot del, okay, plus r prime dot del the whole square by factorial 2 and so on, acting on one another. So you can see that this will be an infinite series. Okay, so first term is 1 by 4 pi epsilon naught integral d3 r prime rho of r prime into 1 over r. 1 over r is can be pulled out because this is not, the integration is over r prime. But what is d3 r prime rho of r prime? This is the total charge. This is charge density. Charge density integrated over the volume is total charge. So I will have this to be total charge Q divided by 4 pi epsilon naught. So this potential is called a monopole. If the total charge is non-zero, so you have something called monopole term. Okay, this is a monopole potential. Okay, so I might call this as phi m of r. Phi m of r is equal to this. M corresponds to monopole. Okay, now let's look at second term. Second term, I will, as you know where I am heading to, I would call it as D of R. D stands for dipole. So 1 by 4 pi epsilon naught integral d3 r prime rho of r prime. Now I would write this with a negative sign, of course. I'll put the negative sign outside. I will write this as x xi prime into del I, that is the dot product, into 1 by r. 1 by r, I will write it as 1 by xj. So this quantity is something that I have to evaluate, and this evaluation is independent of the integration because this does not depend on primed coordinates. This is in terms of unprimed coordinates. But in fact, I have already evaluated this because the first problem that I have looked at today's class is that, right? So this is the problem. Del I square root of xj. And the result is something which I have already known, xi by r cube. So that is what this is. So I will borrow this result, and then I already write it in this class. So this is equal to, so there is a minus sign there, that minus sign. So we know that this is nothing but minus xi divided by xj to the power 3. So that minus sign, this minus sign will cancel. So I will have 1 over 4 pi epsilon naught into, there is an integral V3 r prime rho of r prime into xi prime. So this quantity, when you do this integration, you will get a vector because you have one free index I here. And then we have here xi divided by xj to the power 3 by 2. Okay, so this quantity in this bracket is what is called pi. This is the dipole moment. This is the dipole moment vector. So when you write down this pi dipole potential, you will have 1 by 4 pi epsilon naught pi xi divided by xj to the power 3 by 2. So if you write this in the familiar vector language, this is 1 by 4 pi epsilon naught p vector dot r vector divided by modulus of r cube. Or sometimes equivalently you write this, if you cancel one of the magnitudes of r, so 1 by 4 pi epsilon naught into dipole vector dot r cap divided by r square. So this is the potential for a dipole. Okay, so now let's look at second term just to, this is second term, right? So let's look at third term. So third term is what we will call it as a quadrupole term. Okay. So I would like you to try this. In the third term, I have terms like r prime dot del the square, which is equal to, for one dot product, I will write it as xi prime del I. For the other one, I will write it as xj prime del j. So this can be written as xi prime xj prime del I del j. Now this has to be operated on 1 over r. Okay, so that means 1 by square root of, now I and j I have used, so I should call it as xk. So 1 by square root of xk. Now I want you to calculate this quantity, that is del I del j 1 by square root of xk. So please calculate this. Take some few minutes and then calculate this.